The Internet has changed our existence and has now become our preferred medium of everyday communication. In almost everything we do, we use the Internet. Ordering a pizza, checking a business email, sharing a heartful thought with a friend, sending a picture or thoughtful business idea over instant messaging. To keep up socially and with the news, a click or two brings us any news source from anywhere in the world updated to the minute. We live in the Internet. Immense quantities of information are uploaded and downloaded over this digital ocean, and the content is very much our own. For now, we are all commentators, publishers, and creators. The Internet became a formidable resource for building knowledge and developing business. One can use the Internet to access libraries, encyclopedias, art galleries, news archives, and other information sources from anywhere in the world. In addition to its communicative traits, the Internet has become a vital tool for exchanging knowledge, education, and business. It is not just an information source or a locus where results can be published. It is also a channel for cooperating with other people and groups who are working on related topics. A key issue surrounding Internet use is privacy and security. Today's Internet is a playground for hackers, from insecure communication links to inadequately guarded private business and financial data. Vulnerabilities are everywhere. A quantum Internet based on the laws of quantum physics aims at sinking these troubles down deep to the bottom. Prospective quantum networks sporting full-blown quantumness, where information is created, stored, and moved around in the way of the quantum world, will provide a level of privacy, security, and computational clout that is impossible to achieve with today's Internet. Initially, one expects hybrid forms of quantum computers and network technology that would combine the classic and quantum modules. At the moment, a fully realized quantum network is still a far-off vision. However, recent breakthroughs in transmitting, storing, and manipulating quantum information have brought confidence in the enormous gain in security. The use of qubits built into a quantum network using standard optical fiber to connect small quantum devices located about 50 to 100 kilometers apart will enable us to have absolutely tap-proof communication, secure identification, concealment of location, and secure data processing between the two connection points. To learn about the advantages of the quantum Internet, look at the ways the classic Internet works first. The Internet is a combination of many networks that exchange data with one another using a unique Internet protocol, IP, and domain name server, DNS, address. Through the Internet nodes, the requested data will be transferred to the requested computer. The information is transferred in data packets using Internet protocols. The data is transmitted in bits, the smallest unit being 0 or 1, and bytes. 8 bits equals 1 byte. This implies a binary system of 2 to the x power as a digital base. In a quantum Internet, not classic bits, for example 0 or 1, but qubits are transmitted. This means that the smallest unit qubit can be 0.1 and or 0.1 at the same time. Quantum information is encoded in photons and transmitted via the same fiber optic infrastructure that is being used for the classic Internet. Switches and repeater are different to the classical devices. Terra Quantum has been intensively developing every aspect of quantum computing, quantum security, and the quantum Internet's facilities. Terra Quantum targets to satisfy every need of the customer, ranging from the solution of a particular technical fragment to global technical solutions tailored to every specific demand. We aim at pushing the advance of the basic elements of the quantum Internet to compare with and to exceed those of the classic Internet, first and foremost in terms of simplicity and reliability. The state of the qubit is imprinted in the quantum memory. The measurement device measures the state of the quantum bit. Importantly, once measured, the qubit changes its state. The end node finalizing the Internet connection is the customer's computer or laptop or phone or any other device that is connected to the Internet on which we run applications. it is revealed that end-node quantum computers for most quantum internet applications do not require exceedingly huge quantum computers, but are beautifully served by modest-scale computers comprising less than 10 qubits. This news seems not to generate much excitement at first, yet at second thought makes it immediately clear what a huge advantage in resolving practical tasks this observation implies. As early as in October 2019, Google demonstrated an advantage of the Sycamore quantum processor over classic data centers with only 53 qubits. The quantum internet derives its power from the quantum entanglement of the qubits. Two photon entangled states are generated in the process of spontaneous parametric scattering of radiation from a 325 nanometer helium-cadmium laser in a nonlinear VBO crystal. The pump photon decays into a pair of photons in accordance with energy and momentum conservation, which are also referred to as phase synchronism conditions in the context of the Internet description. These conditions can only be met in a nonlinear crystal due to the difference in refractive indices for two orthogonally polarized light waves propagating in an anisotropic medium. The resulting quantum state of light is characterized by the fundamental quantum mechanical correlations between the photons comprising the pair. As long as photons maintain their quantum entanglement, as soon as one of the photons changes its quantum state, for example, because of the measuring procedure, the state of the other photon changes immediately without any time delay, irrespectively of the separation distance between the photons. Now, the fundamental challenge in transferring to quantum information is that when transmitting the qubit over the Internet, the qubit cannot be copied or cloned. Any attempt to do it, since it includes the measurement of the transmitted qubit's state, will result in a loss of the qubit. Hence, using the quantum internet worldwide means that we have to develop the ability of transmitting a qubit over distances like 20,000 kilometers. One of the limitations of the existing optical implementations of the transmission lines is the comparably small maximum transmission distance, approximately equal to 100 kilometers. We are thus in critical need of the following technical solutions: robust repeater technology, reliable quantum memory technology, reduction of the signal loss during a long signal transportation, future communication networks, a multi-user quantum internet uniting a worldwide multitude of users will require corresponding worldwide distributing multi-qubit states on demand. Finding the optimal configurations of networks that will be distributing these states posits yet another challenge that Terra Quantum is enthusiastically preparing to meet. The immediate problems to resolve include developing protocols and network designs capable of successfully performing in realistic, noisy, and asymmetric emerging situations. One of the possible routes to arriving at solutions to automating quantum communication and designing the future quantum internet is the use of the methods of machine learning protocols. The reinforcement learning approach was able to learn protocols for the performing of teleportation of an unknown state, entanglement purification, quantum repeater, long-distance entanglement distribution,